I'm Paulo Shakarian from Arizona State. A little bit about me, I'm a computer scientist by training, and in computer science I focus primarily on artificial intelligence and machine learning, but with an eye toward application to social networks. And this is what got me interested in evolutionary graph theory, because I was really exploring, well, for many years now, I've been exploring diffusion processes in social networks, and evolutionary graph theory was really captivating to me because, unlike many of the models in computer science, it has some interesting aspects to it, such as non-monotonicity, so your number of mutants doesn't necessarily increase at each time step. Also, the integration of gameplay I've always thought has been a really neat idea. And so me and one of my fellow grad students at the time, Patrick Roos, we were collecting papers on evolutionary graph theory, and we had, a binder full of these papers. And so then we decided back in 2011 or so to write a review paper, and I think many of you have already been looking at this. But it's already a little dated now. It's a couple of years old, but I think it's still a useful starting point. So since writing this, I wrote a second review of work in the form of a short Springer brief called Diffusion in Social Networks. And in this book, we look not only at evolutionary graph theory, but we look at the various different paradigms for diffusion that are seen not only in theoretical biology and computer science, but other disciplines as well. And this book, so as a tip of advice, if you're writing an academic book, especially with Springer, lately they've been letting people upload the entire book to their academic website. And we had that in our contract, so you can see a whole preprint of the book for free if you don't have to pay for it. So, because I'm not anticipating huge royalties on this anyway. So, but anyway, in the book, this outline of different paradigms are many of the things described in the book. And then previously, I've gotten some tutorials at IDGCAI and AAAI, which are major artificial intelligence conferences, on this very topic, where I would have a whole day to go over all these things. And I'm not going to go into everything this morning. I'm only going to pick a few select topics. But what's really neat, to me at least, is you have models such as SIR-SIS that appear in physics and more in the epidemiology than biology. And then you have models on the other end, such as the tipping model, which is shows up a lot in the discrete math literature and to a little bit lesser extent computer science. And things like Kempe-Kleinberg-Tardos, that is, really a big deal in the data mining community. The paper that introduced this, I think, has like 10,000 citations or something like that. Logic programming-based models. This was something that was introduced by me and my advisor, and has since been followed by a few others. The idea here is that we can represent a complex network as not just a series of nodes and edges, but also we have various labels for the nodes and edges, so you could specify which type of relationship, and you can use this information in your diffusion model, or in evolutionary graph theory terms, your update rule or model dynamics, where you can specify things that an individual adopts a behavior if 2 of his close friends or 5 of his acquaintances previously adopt the behavior, and do so with a level of confidence. Evolutionary graph theory, I'm not going to go into that as much or at all today, because I felt that Mark did an excellent job covering that. And today we are going to go into a bit of empirical results and data-driven approaches, which to me are 2 sides of the same coin, but they come from different communities primarily. The empirical results tend to come out of sociology, psychology, even some of the business schools. And I think these papers that these individuals write, a lot of them will be very notable and appear in things like Science and PNAS, but then the results don't seem to trickle down as rapidly as I think they should into, say, computer science, because they're identifying new factors of influence, which is, in my view, one of the key building blocks of creating more realistic diffusion models. And I'm going to touch on that a bit today. And finally, data-driven approaches. This is sort of the computer science analog to the empirical results, where instead of assuming a model structure necessarily, or even a model where there's a lot of parameters to be learned from data, it's looking at, well, how can we make predictions based on certain characteristics, and maybe these characteristics are informed by ideas from diffusion and as well as empirical results. So when I started working in diffusion and evolutionary graph theory, at the time in the, so I finished grad school around 2011, so that's right around the time I was getting really into this stuff. It seemed to me that most of the work was model-driven, and most of the validation of the model theoretic results in computer science were, hey, I have a mathematical model, I think of some fancy and interesting query. Based on that model, I come up with efficient algorithms to answer that query, and I do some tests on social network data, which just comprises of the graph, the nodes and the edges. And around 2010 timeframe, this was the main thing that was available. Since then, what we have seen is a lot of new data where you not only have the nodes and edges of the graph, but you also have information about previously seen information cascades. And by information cascade, I mean you see an initial blog or an initial photograph being posted somewhere in the social network, and you see everyone who has retweeted that or rebroadcast it somehow, so you have an idea of how that thing spreads in the social network. Now there's a whole host of issues with that, and you have to have some domain knowledge about the particular social network you're dealing with, because you want to avoid things like a photo or meme that spreads because it ends up on like the home page of Flickr, for instance, because now network effects is likely not what's causing that to spread to a wide extent. But there's also some heuristics and methods available to overcome some of that. But that's been a little bit more recent development. So since I joined the faculty at ASU about 2 years ago, I have really focused a lot more on empirical study and data-driven approach, not because I want to get rid of the models. I instead want to understand how we can better inform the models, and this is sort of the theme of the talk. So in doing so, we not only can inform the models, but you can also do this the other way around, where you can use ideas from mathematical models to find something interesting about the data. And I'm going to give at least what I think is a pretty interesting example of where we have found this in our work. So if you look at the slides, these are the papers I cover, with the exception of this second paper on violence prediction that's currently under review. All of these are available for download. So we're going to start with a very simple diffusion model, so much simpler than the models from evolutionary graph theory. And this is this notion of tipping. And it was first introduced simultaneously by Thomas Schelling and Mark Grenovetter in the late 70s. Schelling was really looking at it more in terms of spatial population. Grenovetter was looking more in terms of a structured social network. And the idea is simple. You have some parameter k for each node, and when the number of friends of that node who previously adopt the behavior exceeds this threshold, then he adopts. So here the individual had a threshold of 4, and then he turned red. So of course, there's a very natural extension of this to a social network. And so we simply will use the term activated to refer to a node that adopts a new behavior. And so we see in this toy example, nodes D and G, they initially adopt the behavior. And let's say that an individual is activated in this case when at least half of his or her friends previously adopt the behavior. So then right away we see several more nodes adopt the behavior, but that's about it. No more of the nodes that are non-adopters have taken on the new action. So here's the mathematical formalism. We assume a graph. We have a set of incoming neighbors. We have this function theta that is part of the input, and that just takes all nodes and returns a threshold value in the interval 0, 1, and this just simply tells us the fraction of neighbors. And we will use this notation k just to be the actual number of neighbors required to exceed that threshold. And we specify an activation function. We're given a set of nodes v prime. It returns that set of nodes unioned with all other nodes whose threshold has been exceeded due to v prime being previously active. And we can define this for multiple iterations as such. And so here's example. H and J, there are initial adopters.
Can you explain what do you mean when you say activated? I'm trying to understand.
So activated means, so for a given behavior, activated means I've taken on that behavior. So a new node is activated when it takes on that behavior, which happens automatically as soon as the number of his or her neighbors exceeds threshold k. Does that clear it up?
And then what does this threshold mean? Like
Well,
maximum number of friends I can have?
that's the minimum number of friends that need to previously adopt the behavior before I do. So k is the actual number of friends and theta is the fraction. Okay. So H and J adopt, then G and I, and again the process can proceed no further because we see the next possible node that could be activated is C, and only a third of its neighbors are active, and we said in this example we were setting all the thresholds equal to 1/2. So very simple proof, we can show that the number of steps taken to complete this process is order n, where n's the number of nodes. And so that's very easy to show that this terminates in polynomial time. So again, this is much easier than with the probabilistic models where you don't get this result. And we have seen this going to a biological context. We have seen tipping dynamics occur in schools of fish. And this is a paper by Ian Cousins, who I think he's at Princeton now, although he may have moved. And so what they did is they looked at the schools of fish and they looked at where the visual range of the fish and what other fish that fish can see. And based on that, you can have a social network of the fish. And what Cousins found was that when the number of other fish that a fish could see took an action to swim in a different direction, that fish would then adopt it. So they observed the tipping point process happening in this behavior for the school of fish, and based on the visual cues, they were able to show a pretty good model fit. So the problem I became concerned with is the idea, so gamma here, this just returns the this just returns the set of nodes upon the convergence of the A operator. So this just tells you which nodes are active at the end of your process. And the min seed problem is to identify a set V prime of smallest size such that when you run the diffusion process, all nodes in the network have adopted the behavior. And this has been shown to be an NP-complete problem. And there are, of course, variants of this problem. You can have a decision problem, yes, if there's a set of size k such that everyone adopts, you have minimum cardinality, maximum spread, and so on. One thing about this is there has been some work in computer science that looked at a property called submodularity, which essentially is just saying that every time you would add a node, you get this diminishing returns. And this has been shown to work in some of the probabilistic models, but by this example, it does not hold for the tipping model. And the reason being is that if I have node G by itself, and I say the threshold is 2 for all nodes, I don't get any adoption. And the same could be said for node H by itself. But node G and H together, you get this synergistic effect where now you have an increase of 3 nodes. And I show this mainly people familiar with this property often question why didn't it get leveraged in trying to address this problem, and the answer is quite simple. With the probabilistic models, you often get you have a probability distribution over what can happen given the node is previously active, and so you always have this little bit of chance that something will go on, and you don't have to wait for other nodes to be active in order for individuals in the network to have their threshold be exceeded. And then going to more the mathematical sociology side, well, why not pick nodes with high centrality, high degree, and so forth? Well, if you're picking a single node, you have no one's going to exceed their threshold unless it's a threshold of 1, even if that node has a lot of connections. Likewise, if I go through a list of nodes and I pick the most highly central nodes, there's no mathematical guarantee that anyone will exceed their threshold. And you can imagine this if you have a large social network. I have a high degree guy here, another high degree individual here, but if they don't have anyone in common and the thresholds are all greater than 1, and 1 is pretty trivial, it's just a connected component to the graph, then no one is active. So the membership in NP hardness for this problem is easy because the process completes in polynomial time. And for hardness, this is again from the old Dreyer paper, where it can be shown based on a relationship with max K cover. And for those of you who teach mathematics to undergrad, you'll be familiar with this proof technique called proof by picture, where instead of actually proving, I just show an example to hone the intuition, where with set cover you have a family of subsets of elements, and you want to pick a minimum number of subsets such that you cover the union of them covers the most elements of this as possible. And we relate this problem to max K cover by creating a graph that's essentially bipartite, where you have nodes representing sets, and they have directed edges to nodes representing elements. So if you pick a set of and if you have a threshold of 1 and you pick a set of nodes such that they cover all these guys, that corresponds with the solution to this min seed problem in the tipping model. So one way, an algorithm to address this is you could have a set of integer constraints, and we set this up a way in that if you find a vector of numbers in the interval 0, 1, then that maximizes the objective function with respect to these constraints. It corresponds to the solution. But of course, integer programming is also NP hard. And here we have a quadratic number of variables, so it's a big integer program, so it becomes difficult even for a solver. And there have been many theoretical results dealing with this problem as well, limits of approximation and so forth. So what we designed was a decomposition-based heuristic. And decomposition methods they were actually introduced back in the mid-'80s for social networks. And the idea is you want, with original decomposition methods, they were used to find a solution to the problem is, can I find the largest subgraph of a graph such that the degree of each node in the subgraph exceeds a value k. And this largest subgraph is often called the k-core. And it can be found by iteratively removing nodes from the graph. We use this idea of removing nodes from the graph, or decomposition, as a heuristic for this problem. This algorithm here we can show by a simple proof, inductive proof, that the solution returned by the algorithm will definitely be a seed set, but we make no guarantees on the size. So instead of going through the pseudocode, I'll give you an intuition. So for each node, again, we're going to say the 50% adoption. And what we'll do is we'll associate with each node its current degree, as well as this notion of a distance to being tipped, which is the degree of the node minus the minimum number of neighbors that must be active for that node to be tipped. And the algorithm proceeds as follows. At each iteration, we removed, so we call this the distance to being tipped. We remove the node with the smallest distance to being tipped that's not negative. And negative distances we don't touch. And once we remove the node, then we update the distance to being tipped for all its neighbors. So here we remove, I think it's going to be H first, and then I, and J. So notice I'm stripping away nodes. I'm updating this distance to being tipped. And now D has fallen to -1, so it cannot be removed. And I continue to strip away. And I'm left with D and G, and that's what the algorithm returns as a solution. And we can show by proof by induction that this will definitely lead to universal adoption in the network. This is a very quick process. We can code this up with some clever data structures to run in near linear time, which is cool. We have also, in kind of going along the old lines, we've done many experiments with real-world social networks where we would run the algorithm and examine the size of the seed set. And what this chart shows is for 3 categories of networks, so we examined 30 in all. What we varied here is we said every node in the network must have threshold 2 or its degree, if it has a degree of less than 2. And so what we found is one category of networks dealing primarily with social networks, that the fraction of individuals needed for the seed set is very low, or the percentage. So here, even if everyone has a threshold of 10, we can get universal adoption with only 3% of the population. Category B was mostly email networks and some specialty social networks. The fraction of the population that must initially adopt, at least by returning from the algorithm, is a little bit higher, but still you're going about 5 to 10% at worst. In category C, well, these were primarily academic collaboration networks, and the algorithm did not perform so well. And so why is this? Okay. Well, there's actually, we were puzzled by this, but we looked at there were some structural reasons why, and I'll touch on that in a moment. The interesting thing also about this is if you go to the site, and I think it's also in the book too, but we have a paper on this from a couple of years back. We also did experiments where we looked at the threshold as in terms of fraction of neighbors, and these results more or less hold, at least in the size of the seed set. The graphs looked a bit different, but you're still finding very small seeds. And we also looked at the case where we didn't allow you to influence anyone with a very high degree or high page rank score. And we're still able to find small seed sets. And this outperforms all, centrality methods and all this. It's a very robust heuristic in finding a small set of nodes that kick off this process. And it's fast. At the time, this was a 1.4 million node, 5 million edge graph, and using pretty commodity hardware, we were able to find the seed set in under 15 minutes, which was nice. Now, I mentioned about the collaboration networks, so what was so special about them? Well, we looked at a lot of things that we thought might explain, why where we could find the aspects of the network where we could explain why the algorithm fails. So here we have Louvain modularity, which measures is a measurement of a partition for the network. So so if you have a partition of the network and you group it into communities, Louvain modularity, if it's for the optimal partitioning, if it's very high, that means your communities have a lot of social connections within the community and very few social connections between. So when you get toward 1, you're getting more islands. And clustering coefficient, this is the average number of triangles an individual has in their immediate connections. And we found both of these things were high, which was the case in academic collaboration networks. The algorithm found much larger seed sets. It didn't work so well. And this kind of makes sense when you think about it, because academic collaboration networks, it's pretty well understood that they're highly clustered and that small groups of individuals tend to form and be very tight-knit, like the one in this room, for example, but maybe not so well connected as a group to others. So, and we can see this for the NIMBioS audience here, right? So I have a lot of connections in computer science and data mining, but probably not too many of you guys do as well. You might be a biologist with a lot of connections to people in, say, ecology or something like this. And again, it's going to only be a small fraction of people here, so it's not well connected to the other community. The clustering coefficient, I think, is easily explained that, you're a PhD student, you do work with your advisor brings someone else on, you get to know that person, then, you end up working with that individual later on. These things seem to inhibit diffusion because it limits the spread of where the trend can take off to. And so if I have a community that is highly isolated, and I have a good seed set of there, if the threshold is 4 or 5, and that community has only 3 connections to other communities outside, then it's not going to leave that particular group of people too easily. So anyway, so this was some initial work I did on the tipping model. It was pretty well received and all that. Now I'm going to switch gears slightly, and then I'm going to loop around and I'm going to remind you of the tipping model in a couple of slides. So bear with me. So we've also done a lot of work with law enforcement in my lab over the years. And one problem we had is, can we predict individuals who are previously arrested who will commit a violent act? And so this is based on data on Chicago gangs from a partnership we had with the Chicago PD. And we can see that rearrests within the data set we looked at for our district in Chicago, people with 2 or more arrests is pretty significant. Also, based on police data, if 2 individuals are arrested at the same time, we can assume that there is a social relationship between them, and we can create a social network that looks something like this blob. Now, we wanted to predict who in the social network is likely to commit a violent crime in the future, and we also had information to label the nodes as being violent or not. So we could do a nice traditional machine learning experiment. Oh, that's just the visualization. It doesn't mean anything. Yeah. So what we did is we took a supervised machine learning approach, which means for each individual we had associated a vector which corresponded with a group of measurements, often called features in machine learning speak. And we divided the features into different groups. We had some that were based on the immediate neighbors. So these are all graph theoretic based features. We had some based on going beyond the immediate neighbors of the nodes, like some traditional social network measures such as betweenness and closeness. And we also looked at feature groups dealing with time and geography. And we wanted to see how these groups performed, as well as how it compared in prediction against baseline methods that the police were already using. And I bring this up because one of our features that that me and my students decided we'd want to play with was what we called propagation, but this is just the tipping model. So this says if you have a set of violent individuals that you know have been arrested for being violent, and you treat that as an initial set of individuals in the tipping model for some parameter k, where everyone has k as a threshold, you look at how that process proceeds, and everyone who is activated at the end of that process, we label as a 1 with this measure as potentially being violent. But this is not the only thing we use in this approach. We mix it with a bunch of other measurements, and we have more than one k. So in our vector, we have a whole string of k values for different thresholds of if the person is active, if the threshold was 1, or not 1, but 2, 3, and so on. So in our initial paper that we presented back in the summer, this is false positive versus true positive rate. So with a graph like this, you want the curve to be, up and to the left as you look at it. And so what we found is, unsurprisingly, when you have all the features from all the categories, that does best. But previous work in criminology examined temporal and geographic features, which taken by themselves were actually the worst performing, and both neighborhood and network-based features, when taken by themselves, perform much better. So the social network seemed to have some level of primacy and able to predict who the violent offenders were. So this was really good, and I didn't put the chart up on this, but we also handily outperformed the existing method used by the police. And we thought about, well, what to do next. So one of my PhD students started playing around with the results of the data, and he started asking the question, well, why was the machine learning algorithm classifying individuals in a certain manner? And this is an important question because with a machine learning approach, the idea usually, a lot of the research usually is in how do I come up with these features, these measurements that will be predictive, and then I just train a classifier using something existing like logistic regression, random forest, and so forth, and I see how it does in terms of things like false positive rate. So what he did was he looked at the feature vector for all the individuals. Did you have a question? No? For all the individuals predicted as violent, and he plotted them in a hypercube. Here we see a two-dimensional projection of this. And then he ran some unsupervised clustering algorithms to group the predictions based on similarity amongst these measurements. And so he identified 5 different clusters. So then the idea is, well, let's look at each of the clusters and let's look at which features matter most. Cluster 5, the features that matter most are in yellow. Cluster 5, what mattered most were features based on the tipping model. So there was a population of individuals we found in the data set where the tipping model was the primary measurement that was telling us these individuals would be violent in the future. And again, we have these multiple tipping models because each one is with a different assumed threshold. Yes? We think a violent behavior diffused. So we think what happened was an initial group of individuals who are violent kicked off a chain reaction of violence within these communities of individuals. That's what we think happened. So that was pretty exciting. So then we thought, well, what happens if we look at this population and we try to predict individuals being violent based only on the tipping model? Okay? So we don't use any fancy machine learning algorithm. We just say, we take the tipping model, we assume some threshold, we run it, and we assume everyone at the end of the process is going to be violent. How does that do? Well, here we see true positives and false positives. Now, our data set was time series. An inherent difficulty with this data set is when you start getting toward the end of the time series, your false positive rate is going to be higher than it probably is in reality because there's individuals violent in the future that you've predicted correctly that's not included in the data. So here I show for tipping thresholds of 2 and 3, true positive and false positive. And we see we actually get some very precise information here. So green shows the tipping point operator running to convergence. These other lines showing where we limit the number of iterations. But the green lines generally do pretty well. So we see for this period of time, when the data set goes up until late 2012 to mid 2013, we get a large number of true positives, and this holds a little, also holds for the threshold of 3. And the false positives, of course, they are growing, but they're actually pretty small compared to the number of true positives, roughly half in both these cases. So these are interesting. This is an interesting finding because this is some solid evidence that we're seeing that these violent activities are diffusing. You could probably even do better if you had maybe a stochastic version of the model and so forth. And we're considering these kind of things in the research, but we thought this was really neat because we had the model, we thought it was useful, we used it as a measurement to predict violent behavior, and then after that we re-examined how well it did within a certain part of the data. So here we looked at machine learning to identify violent individuals based on measurements and features that came out of a model. Next we thought, can we use machine learning to maybe inform our model a little bit? So one problem that is very much examined within the literature in my field is early identification of viral cascades. So we say if a trend is spreading on a social network and we observe, say, 50 individuals have retweeted a message, can we predict if it'll go viral? Will it go from 50 to, say, 500? Will it go from 10 to 100 or 1,000? Order of magnitude increase. And we could do this with regard to size. We wait till the number of adopters has reached size T, or we can have a time-based. We can just observe the trend spreading for, say, an hour. Now you might think, well, this could be very easy. Maybe I just see what's spreading quickly or what's spreading to a wide extent. But it turns out that these simple measurements actually will get you an accuracy of somewhere in the neighborhood of 30% only. There's plenty of times when something spreads quickly initially and then suddenly dies out. Further complicating the problem is there's this, what you call in machine learning, a class imbalance problem. And here the y-axis is logarithmic, and we're looking at the final size of this cascade of adoption. And the larger you get, you're starting to shrink by, a significant portion of how often these things occur. So if you're using machine learning to address this problem, your portion of the data where the information actually went viral is very small compared to the entire corpus. So there's been some previous work on this. So unfortunately, a lot of studies in machine learning have looked at this problem of viral prediction, and they address this class imbalance by artificially sampling from their data set to give you, say, a 50-50 split or whatever. But then what happens when you do that is your technique breaks down when you bring it to the real world. One approach to this was, well, since the size of the cascade versus frequency follows a power law distribution, maybe you could just predict when things will double in size, and now you have this balanced class. And so there's been a line of work dealing with that. But we use a bit different idea. So in 2012, in the Proceedings of the National Academy of Science paper, they looked at usage of Facebook by individuals who signed on and were influenced by friends of theirs through email. So because Facebook had the information about the people who emailed an individual, and they had data on long-term usage over, I think, a year or 18 months, they were able to see what was predictive in long-term usage. Now, based on the tipping model, you would expect that, hey, the more friends you have send you email invites for the social media site, the longer you will use it. And in this 2012 paper, that was true, but only until about 3 friends. Once you got above 3, it leveled off. What then the researchers who were working on this did is they say, okay, well, let's look at the ego network of the individuals, and let's somehow group the friends of that individual into communities. So one simple way of doing this is to take all connected components of, whose size is greater than, say, 2 or 3. Another way is what we've done in our work is you could run a community finding algorithm on the entire network and label all the nodes as being in a particular community. And there's other ways you could come up with this too. Point being is that it seems natural that you're going to have friends in different social circles, and that's what we depicted on this chart. So up top, this individual is the guy we're interested in, and he has many friends who previously adopted the behavior, but they only exist in 2 social circles. So maybe he doesn't adopt. Whereas individual here actually has less individuals who previously were activated, but they're in 3 social circles, so maybe it's more likely that he adopts. And this is the basic finding of the preceding National Academy of Science paper that these other researchers worked on. So our intuition was, if this information cascade, if you will, that's progressing, when it reaches this initial set of nodes, we look at the community structure in that set of nodes, and maybe that can help us predict if the trend is going to become more widespread. So what we looked at for a given information cascade, we looked at the subgraph induced by it on the entire population, and the graph underlying the entire population was derived on data that in time occurred before any of the other stuff. So it was older data. So we say adopters in red, these are people who retweeted the message. We say non-adopters are individuals who were exposed to the message for a lambda period of time and did not retweet. And we say yellow, the lambda frontiers, are individuals who have been exposed to the message for less than lambda period of time, and they have yet to adopt, so they're potential adopters. And we set lambda equal to 30 minutes. We've done some experiments to show that this is not a very sensitive parameter, but 30 seemed pretty reasonable because about 90% of the individuals in the data set adopt. If they're going to adopt, they're going to do so after 30 minutes. So based on this notion of structural diversity and these 3 different sets of nodes, is we came up with a variety of measurements. So some measurements were based on the number of communities in a given set, so the number of communities in the adopter set, number of communities in your non-adopters, and so on. We also look at Gini impurity, which looks at the number of groups represented as well as the size of those groups. So it behaves very similar manner to entropy. And we actually did a few experiments with entropy and got about the same results as with Gini impurity. And we also looked at overlap, which was essentially intersections between these sets of nodes. So in addition to this, we also had some baseline measurements that if we were looking at an experiment where we observe 50 nodes, and we want to predict if it went to 500, we'd look at how long it took those first 50 to adopt. For experiments where we observed the first hour of adopters, we looked at how many nodes adopted. So both of these are proxies for rate of adoption. So we use this Sino-Weibo data set that's publicly available. It's not ours. It actually came from the database community, and they were using this data set as part of a challenge to see how fast certain graph queries could be run. But the information is useful for many other things as well. Links to this data set can be found in some of the papers on my site. But this gives us, 22 million tweets. Out of that, we have 2 million cascades, and a lot less of those, of course, have at least 50 adopters, but still we're dealing with numbers of samples in the thousands, which is good. So the first thing I'll show is some of the measurements that were more interesting. So this is the Gini impurity of the non-adopters. So if this number is very high, that means that the community is represented by people who saw the tweet for 30 minutes and thought, not too interesting, was very diverse. Okay, so in other words, the tweet was rejected by a diverse group of people. So we see on the x-axis here, this is number of adopters. And this is this is non-viral cascades, cascades that failed to reach a size of 500. This side is viral. So after just 10 adopters, I'm sorry, that's the other way around. This is the viral and this is the non-viral. After just 10 adopters, if the number of individuals who are rejecting the tweet, if this Gini impurity value is very high, then it's being rejected by a large or by a diverse group of individuals. And we can start to see that right away. This value is much lower when the cascade is going viral. And the neat thing is we have this little bit of data very early on at only 10 adopters. And of course this changes because as the cascade grows, the number of people that are connected to the cascade who haven't adopted grows in size and diversity. But early on, we can see a striking difference here in these two measurements. Another thing we looked at was overlap. And we saw, again, with the overlap between adopters and the frontiers differs significantly between the two classes. So throwing this into a classification algorithm, these numbers are reported precision, which is the fraction of samples reported to be viral that were actually viral. And we achieved a precision of about 65%. Recall, we were a little bit above 50%, and this was the fraction of viral cascades out of all of them that the approach could identify. Now these numbers seem a little low, but the number of viral cascades in the data set was less than 2%. So they're both handily outperforming any random selection. We consider this approach right now, we've done a lot of follow-on analysis and comparison with other methods. It still seems to be the most robust approach. Now, what's the problem with it is that compared to other methods such as looking at centrality and things like this, it's a little more time consuming to produce these results because you're generating all these features for each of the samples and when you build the model. However, the results are vastly improved over many other methods, and the closest method to it is actually this yellow one here, but that has the same problem as we do, and that relies on a feature-based supervised learning approach. And we also evaluated this with respect to what happens to precision and recall when we change the definition of what is viral. So the results I showed you for 500. And what we noticed is when we changed the definition of viral, our results stayed pretty steady, previous best, there was more noticeable degradation. Now you see the precision and recall sort of diverge here toward the end, and this gave us an idea, is that what happens when we just change the threshold in training. So we say, hey, we're still trying to predict cascades that go beyond 500, but we label things as viral or not with a different number. And when we go lower in training the model, say to 300, we're improving our recall, we're catching more, and then as we increase, the precision increases, but the recall drops. And this was interesting because you could use this as sort of a dial to trade precision for recall with our approach. So if I care about catching all of the cascades that are about to go viral, maybe I go down here. If I just, and this is more applicable to say something like countering extremism, where I want to see everyone that's trying to recruit ISIS fighters. Or I go on the other end, maybe I'm doing marketing and I want to see, okay, I only want to be assured of the things that are definitely going to go viral, so maybe I need higher precision. We also see that as this threshold changes, the size of the cascade recalls also increases. So even though I'm increasing so the relationship between the training threshold and the size produced isn't necessarily linear, which is also interesting. So as you increase the value, you can sort of fine-tune with smaller values. So again, this was very exciting, and we thought this was a very nice result. And it made us think that, well, hey, if these the structure of the friendship relations that someone has, their social circles, plays such a large role in prediction, does this mean that maybe we should develop models where instead of counting the number of adopters, and that exceeds the threshold, maybe we count the number of represented social circles? So we created a variant of the tipping model where we did just that. We counted the number of communities someone is directly connected to, where at least one person in each of those communities that was in that community and connected to that individual previously adopted. And we compared this method to just picking nodes of high degree, and we ran essentially the same decomposition algorithm. And what we found was at first, just picking the high degree nodes does a little better than the decomposition algorithm. And this was quite surprising to us. This is the percentage of nodes not activated if we take the number of high degree nodes equal to the size of the set returned by the decomposition algorithm. So if you would go with the degree approach, you're only doing slightly worse. And this was surprising. Why is suddenly degree, which in the other case performed very poorly on this problem, why is it suddenly doing very well? Well, if you think back a couple slides ago when we were stripping away nodes, I said, okay, we're going to take the node with the minimal distance to being tipped that's non-negative. You may have noticed that in some of those slides there were multiple nodes with, say, 0 distance to being tipped. And I didn't mention it at the time, but the algorithm is just picking one at random. Okay? You could do multiple runs of the algorithm and take the small seed set. We found that the size of the seed set was more or less stable for that problem when you did the random selection. So we had this non-deterministic choice, and one thing we thought, well, maybe with this problem, if we bring some determinism into that and we break the tie in a little bit more principled manner, maybe we'll start to get better results. And so this is our proposed tie-breaking heuristic, where the intuition is we want to pick not only a node with the lowest distance to being tipped, but we want to pick a node that has the lowest distance to being tipped and causes the least number of other nodes to have a negative distance. So at a given iteration, I pick a node with, say, 0 distance to being tipped, and as soon as I do that and I update the distance for all of its neighbors, if it causes a large number to go to negative, maybe I want to skip that individual and go on to someone else who has the same distance to being tipped. And the idea is the fewer nodes that have negative distance to being tipped, the smaller your solution. So it turns out that doing this does beat the centrality-based approach pretty easily. And we show here with the seed set size with the tie-breaking heuristic compared to without, we're getting seed sets about half the size with this model based on some empirical data sets. So I think I'm stopping a little early, but it can open up to questions. But just to recap, what we talked about today was, I was initially really interested in looking at models, and I decided to see what empirical results could better inform our model. We investigated the tipping point model, and I introduced a heuristic for finding a small group of individuals such that we reach universal adoption. And then we found that using the model itself was a very useful feature to predict violence in a criminal gang network for law enforcement. When we investigated why our approach was telling us this, we found that the tipping-based features were particularly effective, and for a given population, it alone did a pretty decent job of prediction. Then we shifted and we looked at how can we predict when something goes viral, and the features that we showed were very helpful in doing this were features based on this notion of structural diversity, so examining the community structure of the individuals who adopted the trend. And we thought that this would inform a new model that we started playing around with that is again, a deterministic tipping variant. And we found that we can also have some nice heuristics that can get us small sets for the initial seed set of nodes. Now, where to go from here? Well, what does this mean for things like evolutionary graph theory and games on graphs? Well, maybe we should look at or maybe we should look at rules where you update the strategy based on the community somehow. One work that has investigated this has gone a little bit in this direction was the work of Karina Tarnita, who I think was one of Noak's postdocs, right? And she was looking at evolutionary graph theory with respect to a hypergraph. It's not quite the same thing as what I'm advocating here, because there might be people in an adjacent hyperedge to you that you don't know and can't really influence you. So we're saying that maybe you shouldn't just have the graph, but you should also have some sort of partition of the nodes in the graph. In our research, the partition of nodes we used still comes from the graph topology itself, as did with the results from Uganda. We just used a little bit different method. But we've also done some experiments to show that the method at which you use to find the communities on the graph doesn't really affect results in a very major way. Effectively, you just want to be sure that the communities of individuals in the ego network are tightly connected somehow. So anyway, this concludes the talk, so I'll open it up to any questions.